All right, factoring special products and perfect squares, difference of squares. So let's factor completely, and if we can't, we're going to state prime if it doesn't factor. So let's do the first couple here. How about number 1, number 3? Oh, how about number 8? Okay, so x squared plus 10x plus 25. So you can, as I mentioned in class, we can go ahead and use our pattern to do that, or, and I'll be honest, this is the way I'm going to recommend you do. I mean, why memorize the pattern when our old way works just as efficiently, pretty much, on these? It doesn't save us a whole lot of time to recognize the pattern. So can I find factors of 25 to sum the middle term? Well, sure. 5 times 5. So this is going to be x plus 5 times x plus 5. And we can write that as x plus 5 quantity squared. And once you do a bunch of these, if you go into higher maths, you go into pre-calc, calc 1, calc 2, or any of those, you'll end up wanting to go straight from here to here because you'll do these quite a bit. And you don't want to have to do this every single time. You begin to recognize patterns. Let's try this one about the 100. So can I find factors of 100 that sum to that middle term? Well, sure. 10 times 10. So this is going to be t plus 10 times t plus 10, which is t plus 10 quantity squared. And again, this is the pattern. These two are perfect squares. T squared and 100 are perfect squares. The middle term is the product of these doubled. If I take the square root of those, the square root of t squared is t, the square root of 100 is 10, and then I multiply it together and then double it, I get that term. That's a lot to think about when you're first learning these. So this way here works pretty well as we're going through. Let's look at number 8. Now, where this technique does come out fairly nice is when you see something like this. When these numbers, see here, we just had a plain old t squared. Notice this right here. Perfect square, 25, t squared. 36 is the perfect square. What's the square root of 25? 5. Square root of 36, 6. What's 5 times 6? 30. I double it, I get 60. Boom. So I automatically know this is where that technique saves some time. This is 5t plus 6 quantity squared. There's one thing I would not want to do, I'll be honest. I would not want to do the AC method on this. 25 times 36? I don't want to do that. Because then I got to find factors of that to sum to 60. That's kind of a pain. So this is where that pattern of a plus b squared, a squared plus 2ab plus b squared. Let me rewrite that. A plus b squared. A squared plus 2ab plus b squared. Okay, so we saw this. That's what that is right there. And so we know it's going to be that. Okay, let's do a difference of squares. And as I'm sure I mentioned in class, when you go into classes that aren't like teaching algebra, they are maybe using algebra. I've noticed, just as I've tutored before, like in advanced finance classes or economics and biology, physical science, when they use these equations to model certain phenomenon, it often ends up being difference of squares. Now, my theory is that they don't really want to teach you how to factor when a is not equal to 1. It takes quite a bit of time. It's kind of tedious. They want to focus on the concept that they're working with. And so I've noticed that often these problems come out as nice difference of squares because those are relatively easy to factor. So let's do a couple of these. 11, 12, and 14. So we have x squared minus 25. So recall, my difference of squares, a squared minus b squared is a minus b times a plus b. So this is the difference of squares. These are both perfect squares. And so I'm going to have x minus 5, x plus 5. Now you can FOIL this out. X times x is x squared. X times 5 is 5x. Got a minus 5x and a minus 25. Well, these middle terms are going to cancel out. And I'm just left with x squared minus 25. That was my check. Let's not do 12. Let's do a little harder than that. How about number 17? So I'll come down here to 14 first. The 4x squared minus 9. So we should recognize these are both perfect squares. So this is going to be 2x minus 3, 2x plus 3. We're just taking the square roots of each of these. Square root of 4 is 2. Square root of 9 is 3. About 17. Square root of 36 is 6. So this is going to be 6y. Square root of 49 is 7. So 6y minus 7. 6y plus 7. The difference of squares are much, much easier than their counterparts when we're factoring trinomials. How about 18? Wolf in sheep's clothing right here. Pause the video here, see if you can do that. You may not have paused it. That's okay. What do we notice here? You may be tempted to try to factor this, but what do we notice here? Is this a difference of two squares? A sum of two squares, which we cannot factor over the real numbers like this. So this one is prime. Hope that helps.